topological Hochschild homology and integral p-adic Hodge theory by Bott, Morrow, and Schulze. So on the archive. And yeah, I guess there are many other many other sources as well that are also relevant. And so we'll try to talk about some of them. Okay, so maybe let me get started by just saying some things about de Rham cohomology. So we know that, right, so de Rham cohomology. If you have a smooth manifold, you can compute its singular cohomology as the cohomology of the de Rham complex. So that's a cochain complex that you write down, where in degree I you have the vector space of smooth I-forms, and the differential is the de Rham differential. So this, you can compute the singular cohomology with real coefficients using differential forms. So now let's say you have instead an algebraic variety over the complex numbers. So let's say let's replace M by X, which is going to be a smooth algebraic variety over the complex numbers. And let me assume that X is affine. So X is arising as a spectrum of some ring R, where R is a smooth algebra over the complex numbers. So R is smooth over the complex numbers. So an example to keep in mind is R is C brackets Z plus or minus 1. And so if we have, right, so if we have a smooth variety over the complex numbers, we can associate, so we can associate this, the space of complex points. So X, the C-valued points of X, is a complex manifold. And in the example, so if R is C brackets Z plus or minus 1, this produces the associated complex manifold is just C cross, so C minus the origin. Okay, so if we're in this type of situation, we can work with not we can work with a purely algebraic version of de Rham cohomology. So instead of working with smooth differential forms, we can work with algebraic differential forms. So in this case, can work with the algebraic de Rham complex. And right, so how is this defined? So definition, if R over C is a let's say a smooth algebra for now, then we can define a commutative differential graded algebra, so commutative DGA, which I'll call omega R over C star with a differential D. And so this is the complex, well, in degree 0, you just have the ring R, and then degree 1, you have algebraic 1 forms of R over C. So that's the module of Kähler differentials of R over C. That's a finitely generated projective module in this case, because we have a smooth algebra. And then we just continue and take a second exterior power, and so forth. So we can write down a commutative differential graded algebra in terms of algebraic 1 forms. And maybe, right, so an example is if we take R to be the ring C brackets Z plus or minus 1, then in degree 0, we have C brackets Z plus or minus 1, then we have de Rham differential mapping to C brackets Z plus or minus 1 dz, and the differential is sending d of z to the n to n times z to the n minus 1 dz. So for example, that's what we get in the case of C brackets Z plus or minus 1, the punctured affine line. And right, so we can consider this algebraic de Rham complex, and we can consider its cohomology. So can define the algebraic de Rham cohomology. Algebraic de Rham cohomology. So let's write this H upper star dr of R over C to be the cohomology of this DGA. So for example, well, if we look at our previous example, if we keep going back to this example of R equals C bracket C plus or minus 1, well, what do we get? The algebraic de Rham cohomology. Well, in degree 0, the only cycles are going to be just the constant, z to the 0. And in degree 1, well, z to the n, in cohomological degree 1, the only thing that's not hit by the differential is dz over z. So h upper star dr is c for star equals 0, and it's c, and really c times dz over z, or d log z, for star equals 1. So that's the algebraic de Rham cohomology in this case. And so, of course, you'll notice that the algebraic de Rham cohomology, which is something that were done purely algebraically, it's way smaller than the smooth de Rham complex, is actually giving you the answer you want. So note that the topological cohomology is also this, because the associated top space is just the punctured plane. So the associated space is C cross. So that's good. And in fact, this turns out to work in general. So this is a theorem of Grothendieck. And it states that if R over the complex numbers is any smooth algebra, such as the one we just considered, then there's a canonical isomorphism between the algebraic de Rham cohomology of R, or maybe I should really say spec R, relative to the complex numbers. And this is canonically isomorphic to the singular cohomology of the complex manifold, spec R, the C value points, and cohomology with complex coefficients. So there's an isomorphism like this. Yeah, so this is, I guess, is a theorem that uses some non-trivial, it actually uses resolution of singularities. But yeah, so it's saying that if you have an affine variety, you have a really algebraic way of writing down its de Rham cohomology. You can also generalize this to a non-affine variety, but then you have to, but I guess then the issue that you run into it is that the bundle, the algebraic vector bundle of differential forms itself has higher cohomology, so you have to take some hypercohomology instead. So just say it can also generalize to non-affine varieties. Right, maybe I should also mention that another part of the theorem is that the break finite, which is very much not obvious from the definition. Okay, so maybe right. So this is maybe one of the starting motivations for this this series of talks. But maybe you're wondering sort of why do we care? We already know what cohomology is. Why does it help us that we can do it purely algebraic? Well, one reason that it helps us is that the notion of algebraic de Rham cohomology, it doesn't really depend on the fact that we're working over the complex number. So, sorry. So if X is a smooth variety over a field K, one has the notion of algebraic de Rham cohomology. One has the notion of algebraic de Rham cohomology, which is defined similarly. So, for example, if R over K is a smooth algebra, can define the algebraic version of the de Rham cohomology of the de Rham complex. So maybe can state this as a definition. So definition: if R over K is a smooth algebra, let me characterize it by a universal property. So if R over K is a smooth algebra, the algebraic de Rham complex omega star over K with its differential D it's a commutative differential graded algebra such that there exists a map from R into omega 0 of R over K, which of course is just R. So this is the identity map. Well, so that's the first piece of structure. And the second piece of structure is that it's strictly commutative. So I said it's a commutative differential graded algebra, and that means in particular it's graded commutative. But what we really need here is that it's strictly commutative, which is that odd degree elements square to 0. So odd degree elements square to 0. And then with respect to this, the de Rham complex is initial. So the algebraic de Rham complex is initial for the structure. So it's the initial strictly commutative differential graded algebra, which receives a map in degree 0 from R. Right. And so this makes sense over any field. And so you get some sort of, cohomology theory for varieties over for any field, let's say smooth varieties. Okay, so that's good. So maybe one of the reasons that people wanted these cohomology theories was to be able to count points was actually to work with varieties over finite fields, and then to talk about counting points. So one reason to want cohomology theories is to count points for varieties over finite fields. Because you count points by taking the trace of Frobenius, traces of powers of Frobenius. And right. So if you're an algebraic de Rham homology, and right, so in general, one of the motivations for cohomology theories is that you want to do things like count points on algebraic varieties in over a finite field. So for example, this is one of the reasons that L-adic cohomology was invented. So de Rham cohomology is also some sort of like cohomology-like theory. It's also something that you could try to use. So because say you have a variety X over Fp, you can consider its algebraic de Rham cohomology in the same way. So de Rham cohomology of X over Fp. Sorry, can people read this? Is that readable? I'll write really big. Okay, but so there's a problem if you're trying to count points using this, because normally you count points as a trace of some Frobenius operator, but this is an Fp vector space. So if you try to count points using a trace, you're only going to get something information mod p. So trace only gives mod p information. So right. Right, so this is something that you can try to. So this is one of the reasons the theory of a more refined theory called crystalline cohomology was invented. So there's a more refined theory called crystalline cohomology. Was invented to solve this problem. So crystalline cohomology has the property that if you input a variety over Fp, what you're going to get is not an Fp vector space, but a Zp module. So it's going to produce a Zp module instead of an Fp vector space. So crystalline cohomology is some cohomology theory, and it has the property that when you reduce it, so it's a cohomology theory which takes values in Zp modules, and if you reduce it mod p, in the derived sense, you're going to get de Rham cohomology. So it's a lift of de Rham cohomology to Z. So I guess one of the things that I wanted to talk about in this mini course is this work by Bott, Morrow, and Schulze, which is showing that you can recover, for example, you can recover the theory of crystalline cohomology by thinking by sort of a general procedure that starts with this theory of topological Hochschild homology. So this is a version of Hochschild homology, which I'll say something about, that uses some, well, in the setting of spectra, setting of spectra rather than gene complexes. And what's sort of remarkable is that doing things over spectra, doing this topological version of Hochschild homology actually sort of gives you a retro theory and lets you, for example, recover the theory of crystalline cohomology. And well, I guess I probably won't say too much about this in the mini course, but I think what they were really after is that formally many of the similar manipulations produce new cohomology theories when you start with something not defined over FP, but something that's defined in mixed characteristic. So the motivation for BMS is to actually build new cohomology theories. In these lectures, maybe I'll focus on sort of the special case of FP algebras where it recovers the theory of crystalline cohomology. Okay, so let's see. Hopefully, right. Okay.
Oh, yeah, probably a little larger may be better.
Okay, I'll write as large as I can. Thanks.
Okay, yeah, thank you.
Yeah. Okay, so maybe next I wanted to say some things about Hochschild homology. So Hochschild homology. So Hochschild homology is a general construction that, well, I'll talk about Hochschild homology in the setting of rings over a field. So let K be a field, and R over K, let's say a commutative algebra. So then the definition is that the Hochschild complex of R over K is the derived tensor product of R with itself over R tensor KR. So geometrically, I guess geometrically you're supposed to think of, so R tensor KR, R is a commutative ring. So R tensor KR maps to R via the multiplication map. And right, so you form this sort of derived tensor product. So you can also define the Hochschild homology groups to be the Tor groups. Right, so this is, so geometrically you can think about this as, this multiplication map is dual to the diagonal embedding. So geometrically you're supposed to think of this as some sort of, if R is corresponding to a variety, you're supposed to think of this as a derived self-intersection of the diagonal. So of the variety intersecting itself and the variety cross itself via the diagonal. So this is sort of a general homological construction that you can do. And why is this? Well, so this is sort of the starting point. And what does it actually look like? Well, the starting point is the following basic theorem of Hochschild, Crystalline, and Rosenberg, HKR theorem. So the HKR theorem states that if R over K is a smooth algebra, then Hochschild homology recovers something that we were just talking about. So the Hochschild homology groups of R over K are canonically isomorphic to differential forms on R over K. So canonically, the Hochschild homology is a canonical isomorphism, and this is really an isomorphism of graded rings. So I guess I should write it. Iso graded rings. So right. So this sort of general homological construction produces differential forms. And maybe I should also say that one of the reasons that people were interested in Hochschild homology is the definition of Hochschild homology. Actually, you can define Hochschild homology for a non-commutative ring, or even for a category. So if you define Hochschild homology for a category for a non-commutative ring, it produces an object, it produces a chain complex. It produces an object in the derived categories of K vector spaces. And it's still a similar derived tensor product. You can also write it as you can also write down a very explicit chain complex via the cyclic bar construction. So it's something, it's a pretty explicit construction. So it makes sense for non-commutative rings as well. And that's sort of interesting because, well, on the right-hand side, we're seeing that for a smooth algebra, it's recovering differential forms. Differential forms are something that live in the commutative world. So I mean, one reason that there was interest in this type of structure is that it's really a non-commutative invariant, but it's close to things like cohomology. Okay, so I haven't so there's this isomorphism. This is an isomorphism of graded rings, but we were interested in de Rham cohomology. So I was talking earlier about de Rham cohomology of a ring over K, so a smooth algebra over K, and right now I've written down differential forms. So I guess it turns out that by thinking about Hochschild homology, you can also think about not only differential forms, but also the de Rham differential. So I think this is due to Kahn and Seigen, and the idea is that so can also recover the de Rham differential. And the idea is that the Hochschild complex of R over K is naturally equipped with an action of the circle group. So it has an action of the circle group S1. So, and explicitly, the circle action will give you a differential on the homology groups, which recovers the de Rham differential. So maybe I should say a little bit about the circle action and what this means. Right. And so let me just say it in the commutative case. So what is the circle action on HH of R over K? Well, HH of R over K, it's some derived tensor product. And the idea is that, well, so by definition, this is a derived tensor product of R with itself over R tensor KR. And the idea is that if, let's say you're working with commutatives, and we're working with commutative rings, and the idea is that you can describe this as a homotopy pushout in the world of simplicial commutative rings. So all these objects naturally live in the homotopy theory of simplicial commutative rings. Simplicial commutative rings, and what this construction is doing, well, sorry, so a tensor product, if you're in simplicial commutative rings, a tensor product is just a coproduct, and a relative tensor product is a pushout. So this is the pushout in simplicial commutative rings of, well, R tensor KR, which is a coproduct of R with R. And then over here, you have this relative tensor product, which is the Hochschild complex of R over K. So the idea is that you can do this construction in the setting of simplicial, you can do all this entire construction in the setting of simplicial commutative rings, and you can describe it as a pushout in the category of simplicial commutative rings, or, well, I should say a homotopy pushout like this. And maybe I should say simplicial commutative rings over the base ring K. It does depend on the base field K. Right, but so this is exactly, I mean, this sort of diagram is exactly how you form the circle. So, I mean, the circle is a homotopy pushout of 2 points mapping to a point in 2 different ways, and then you get the circle. So the conclusion is that the Hochschild complex of R over K is a tensor product in the homotopy theory of simplicial commutative rings of K algebras with S1 with R. So this is due to McClure, Schwansel, and Vogt, maybe also in the setting of topological Hochschild homology. But in particular, this is telling you that there's a circle action which is coming from this factor. So maybe more precisely, let me say what this formula really means. What this formula means is that you can give the following characterization of the Hochschild complex with a circle action. So there's a characterization which is that the Hochschild complex of R over K is an object of the homotopy theory of simplicial commutative rings, and it has an action of the circle, and it has a map from R into HH of R over K. There's always, I guess, for a commutative ring, there's always a map from R to its own Hochschild complex. And then the claim is that HH of R over K is universal for the structure. So that's what this formula that you're tensoring with the circle means. It means that it's sort of the free, it's a free thing which receives a map from R in the world of simplicial commutative rings and has a circle action. So, right. Cool. So, by the way, I should say this should look sort of reminiscent of the universal property of the de Rham complex. This should look very reminiscent of the universal property of the de Rham complex, which was a universal commutative differential graded algebra with a map from the ring that you started with. Okay. So now let me say a little bit more explicitly what the circle action is doing at the level of what the circle action is giving you. So explicitly, well, I mean, in any homotopy theory, it makes sense to talk about a circle action on an object or any topological group acting on an object. And if you're in chain complexes, so if M is a chain complex over K with a circle action, then in particular that gives you a map from singular chain from the circle tensor over K with M back to N. So that plus some homotopy coherence is essentially what a circle action is in this context, on a chain complex. And now if you have this type of map, well, you can take the cup product or cap product with the fundamental class in the homology of the circle. So this gives you a map from the homology of M to the homology of M where you've shifted the degree by 1, and that map is take the cap product with this fundamental class in the homology of the circle, and then apply this action. So if you have a circle action on a chain complex, it gives you some operator on the homology, and this is actually a differential. Okay. So in particular, if you have a circle action on a chain complex in an object of derived category, its homology comes with a differential. And note that it's also a differential. It's sort of going in the opposite direction. It's going from homology like Hn to Hn plus 1. So it's going opposite to the differential on a chain complex. Okay. Also, it's a differential on homology rather than on the chain complex. Okay. Right. So I guess the claim is that if you sort of unwind all of this, what the HAR theorem is saying, so HAR is saying that if R is a smooth K algebra, then when you take the Hochschild complex of R over K, well, so this is an object, this is a simplicial commutative ring with the circle action. This is acted on by the circle. So you get this differential, this extra differential epsilon on the Hochschild homology groups of R over K. So you get this extra differential group, which I'll call epsilon, which is coming from the circle. And the claim is as a chain complex, or even as a differential graded algebra, this is the same as the de Rham complex. So somehow it's nice, the universal property of the Hochschild complex, when you take homology groups, also turns into the universal property of the de Rham complex. So this is only true for a smooth algebra, but so it's a nice clean statement. Okay. So let me say some more things related to this. So if you're given a circle action, so we just talked about how you can think about the Rham complex as coming from the Hochschild homology groups of the smooth algebra, plus this differential that you get from the circle action. But there's also something else that you can do, which is maybe a little bit more refined, homotypical related to this, and that's taking the S1 tape construction. So general construction. The general construction is that if you're given a circle action, so if S1 acts on some object M, then say in the derived category, you can form its S1 homotopy fixed points and S1 tape construction.
Sorry to interrupt you. It seems there's a question.
There's a what?
There's a question from.
Oh, okay, sure.
Yeah,
what was the question?
No, I unmute. Like.
Okay.
I was just going to ask, if you look at a finite subgroup of S1.
Sorry, I didn't catch that.
If you look at a finite subgroup of S1,
how
does that act? Does it act in a non-trivial way? Well, presumably on the object in the derived category, it's acting in a non-trivial way.
Yes.
Maybe not on the homotopy.
Well, if you have a finite group action, right? So so the question was, you have a circle action on some object in the derived category, and the question is, right? So let's restrict to the pth roots of unity. Let's restrict to the pth roots of unity sitting inside the circle. What is that? What is that action doing? Well, we said that a circle action is giving you a differential on the homotopy groups. What is the mu p action doing? And right, so the mu p action is going to be non-trivial in general, but it's not going to be something you can see on homotopy groups, because if you have a mu p action, you get an automorphism of your chain complex just by pick a p through of unity. That gives you an automorphism of your chain complex, your object in the derived category, and that gives you an automorphism on homology. But the point is that automorphism is homotopic to the identity, because mu p is sitting inside the connected group S1. So the action by mu p is non-trivial, but the action by every single element is homotopic to the identity. But somehow there's some non-trivial homotopy coherence in that, so it's not a trivial action, but you don't see anything on the level of homology groups. So
thank you.
Okay. So right, so there's a general construction. You can form the S1 homotopy fixed points and the S1 tape construction. And so the idea is that the first approximation, you're supposed to think of this S1 tape construction as, literally take the homology groups of M with its differential epsilon, with its differential that you get from the circle action, and then consider that as a chain complex, and then make that 2 periodic. So it's 2 periodic. Well, sorry, this is really the first approximation. We're supposed to think of it that way. Except that taking the S1 tape construction is sort of a homotopy invariant. It's a homotopical construction. It's an exact functor. It's usually you don't want to go through something like take homology groups and take the associative chain complex in this type of business. But the first approximation, you can think of it that way. And so that leads to the definition of periodic cyclic homology. So the periodic cyclic homology of R over K is defined as you take the Hochschild complex of R over K with its S1 action and take the S1 tape construction. So it's this sort of general construction on the Hochschild complex. Right. So the idea is that, well, you should think of the Hochschild complex as like differential forms, and you should think of the periodic cyclic homology as something like the Rham cohomology, except that it's 2 periodic. So you should, that intuition is is by this sort of other intuition about the S1 tape construction that I just wrote down. And yeah, so you should think that. So idea is that this is something like, so this should be something like the Rham cohomology. So let's say it's related to the Rham cohomology, but to periodic. So let me also say that this is something, periodic cyclic homology is something that actually makes sense, not just for commutative rings, but again, it's a non-commutative invariant, so it makes sense for categories. So it's a non-commutative invariant. And maybe finally, I should also say that, right, so in characteristic 0, this idea turns out to be true. So if K has characteristic 0, then if R over K is smooth, then the periodic cyclic homology of R over K is in fact naturally isomorphic, or quasi-isomorphic, I should say, to periodic Rham homology. Sorry, let's do the good one. Okay, so I guess I'm just about out of time. So maybe we'll start something new here. But essentially, the point of what I wanted to try to cover in this series is in the work of Bodmer and Schulze. The idea is that you want to carry out a similar type of construction, but now you don't. So this is all very classical, but you want to carry out a version of this where you replace. Well, first of all, you replace Hochschild homology with topological Hochschild homology. So in other words, I guess I'll talk about this next time. It's Hochschild homology where you replace the base field K by the sphere spectrum, and formally it's quite similar. And you can similarly define a version of periodic cyclic homology where you replace the Hochschild complex with THH. And so then you got something called topological periodic cyclic homology. And right, so the theorem is going to be, so the Bodmer-Schulze theorem is that, so let me just say, so the BMS theorem. So the theorem is that if you're in characteristic P, you can replace the periodic cyclic homology by this other construction PT, which is the S1, which is going to be the S1 tape construction on THH. And you can recover, instead of Rham cohomology, you can recover crystalline cohomology. And so maybe more, furthermore, you can, if you do this in mixed characteristic, you can recover these p-adic cohomology theories, these AN cohomology theories that that BMS have also defined. So you can build new cohomology theories using THH. So that's about all I wanted to say for, I guess we're just run out of time, but maybe also in the lectures I'll say something about one of the other motivations for thinking about THH is that it lets you do a lot of computations in algebraic K theories. So it's also a different and that's where the relation to a smaller construction called topological cyclotomic comes from. Okay, so I think I should stop here. Again, I'm really sorry about the technical difficulties, and by next time hopefully that's going to be all sorted out. So thanks for listening.
Yeah, I already unmute everyone, so like thanks for yeah, now any questions? Yeah, so feel free to ask any questions to Akhil.
What was the point of taking this S1 tape construction rather than just, let's say, homotopy invariant? What would you get if you did that?
So here's one reason. Sorry. So here's one reason. So I guess for example, we want to talk about something like crystalline cohomology. And so one of the things that's sort of surprising about crystalline cohomology is that you're starting with an algebra over FP, and crystalline cohomology is gonna produce something which is not p torsion, it's a ZP module, and you can use it to do things like count points because it's not torsion. So if you were just to do something like take homology groups in the differential, if you start with something p torsion, you're still going to get something p torsion. But when you take the S1 tape construction, there are a lot of non-trivial extensions that happen. And so the theorem is, in fact, that even if you start with something in characteristic p, when you do this S1 tape construction, you'll get something that can be torsion free. Because what I said is really true up to a spectral sequence, and then there are lots of extensions. So sorry, so maybe just to say one more thing, like I guess the point is going to be that if you take, let me be honest. Right, sorry. So I guess the point is that when you do this construction of Hochschild homology, but let's just even say like FP over FP, and take S1 tape constructions, you're getting something which is 2 periodic FP. But when you do this for THH, when you take THH of FP and take S1 tape constructions, you get something which is ZP, where you've lifted it to characteristic 0. And so the point is that you can only do that if you had this sort of homotopical construction of taking an S1 tape construction. You couldn't do that if you were just taking homology groups with the differential, because then that would not be able to capture these types of extensions, which is sort of important to the theory.
But I guess you can take, once you apply the tape construction, there is a way to take some kind of, well, there's two sort, I mean, the resulting thing has 2 homotopy groups, right?
Sorry, say that again.
Is it true that after I apply the tape construction to my complex or whatever, then the resulting object, I can extract 2 kind of homotopy groups from that. But these are just like the. Does that make any sense?
Oh, I didn't quite follow. You're saying you can extract 2 types of homotopy groups?
Is it true or not that if I have something with an S1 action, I take it, the sum of all its even homotopy groups, for instance, then that is an invariant which can actually be got at from its S1 tape construction. Right? That invariant factors through tape S1 construction, or is that not?
Wait, sorry, you're saying you can take the odd and even homotopy groups of the S1 tape construction. I mean, that is actually what's going to happen.
Yeah,
the point is
that's basically the question I'm asking. But you haven't done this yet.
I don't, sorry, I'm not sure I understood. I guess, sorry, right now I haven't taken I've taken homotopy groups only to state the HAR theorem, but I want to take homotopy groups only at the end otherwise.
Right, so you applied the tape construction, but you haven't said anything about homotopy groups that could be extracted from this.
Well, so I guess we're going to want the homotopy groups of the tape construction, but I think the idea is that you should think of, so the idea is that you should think of the homotopy groups of the tape construction as something like, so if you have an object M with a circle action, then the idea is that the homotopy groups of the tape construction, the first approximation, you should think of that as take the homology groups of M with the differential, and then take the cohomology groups of that complex, and then make it 2 periodic. But in general, they're going to be sort of extensions.
Kind of the situation I had in my head, but basically you're saying that's only first approximation, and there's more.
Yes, it's only a first approximation.
Okay, so are there more questions? Yeah, you can unmute yourself, ask questions. So if there's no more question, I'll unmute everyone and let's thank the speaker again.
That was sort of the climb on.
Yeah, so I guess hopefully to see you guys on Thursday for another mini course.